Okay, this is the review session for the third midterm. The material covered is from chapter or week 8 on the energy equation, dimensional analysis, which we did in week 9, and then pipe flow, which we covered in weeks 10 and 11, but 11 was pipe networks, and so this is not a pipe network in this particular case. So again, there are 3 questions. The first question includes the energy equation. It's a pipe flow question, and it's a type 1, where velocity is prescribed, and you have to calculate the other features of the flow system, maybe Reynolds numbers and flow drops, head losses within the system. There's always, and this year is no exception, a Buckingham PI dimensional analysis question, not just calculating dimensionless groups, but also applying them in some kind of form of similitude. And there's a second pipe flow question, again, not a network, and again, a type 1 problem. So these are the areas, at least for the scheduled exam. And certainly all exams are taken from weeks 8, 9, and 10 together. Okay. So the material that we talk about today should be enough to get you through the test. It should cover all the expressions that you need. The energy equation. I think you know. I guess the important things to remember are that you write it between an upstream and a downstream location. It has to be that way because of the signs of the energy losses or gains within the system. So upstream is 1, downstream is 2, velocity in the pipe is given, and it's just P1, pressure 1 over unit weight of the fluid, plus the elevation of that point, plus its velocity head, plus any pump head that you put into the system. And you can equate that with the downstream conditions, which are just the pressure head, the elevation head, the velocity head that is downstream, and the head losses within the system. So of these, the pump head is positive if it's input into the system. So in other words, is a pump. It's negative if energy is extracted. In other words, a turbine. And you can relate the magnitude of this pump head to a power, if you like, just by using the expression that the pump head is equal to the power in watts divided by the mass flow rate times gravitational acceleration, or the power being equal to the mass flow rate is just the density times the volumetric flow rate times g. So this term here is merely representing mass flow rate, as you know. So that's no great surprise. In this expression, the head losses we know are for minor head losses, such as in fittings and elbows, are the head loss is equal to some loss coefficient K sub L, which are usually given if you need it, rather than needing tables, multiplied by the velocity head within that part of the system. If you don't know what that is other than the pipe going into it, you assume it's the velocity in the pipe. And the major losses are the losses that are incrementally small but occur over a long length of pipe, and those would be given by a friction factor, the length of the pipe divided by its diameter, and the velocity head term within that pipe. So those typically define the behavior in a pipe. I suppose we also know that within the pipe we can define friction factors according to the velocity. the length of the pipe over which flow occurs, its diameter as we go through the pipe, and also the magnitude of the roughness on the wall, which is often defined as epsilon. If we know the flow rate, we can always get the velocity by dividing the volumetric flow rate by the cross-sectional area, whatever that cross-sectional area is. Obviously for a circle, it's relatively straightforward. And for pipe flows, we use the Moody chart, which allow us to be able to define the magnitude of this friction coefficient for a variety of conditions. And so the Moody chart is always defined in terms of a Reynolds number, which is velocity, flow velocity, the density of the fluid that's flowing, and a characteristic dimension, usually the diameter of the pipe, divided through by viscosity. And the friction factor is a non-dimensional term, which is the term that goes, the scaling term, if you like, that defines how much head loss occurs on the system. If we look at the typical behavior of the system, then around something like a Reynolds number of 2000, we go from being laminar to turbulent across this boundary, which is an important boundary to understand, I guess. And the behavior on the different sides of this are that the frictional losses in the turbulent regime are a function of the relative roughness, and they scale with that. And within the laminar regime, they're independent of roughness. So roughness independent. And this trajectory here is actually the friction factor being equal to the Reynolds number divided by, it's the reciprocal of that, 64 divided by the Reynolds number. And so in this regime, roughness doesn't matter. You can always get the friction factor from the Reynolds number, and the Reynolds number is a function of the diameter of the pipe and the fluid characteristics. So you can always get that from that system. So that is pipe flow. I guess I did mention above that the problems are so-called type 1 problems, which means that typically velocity is known, and from that you can calculate a Reynolds number, and from that Reynolds number you can calculate a friction factor through Moody, and then solve the system using that. So that takes care of at least 2 out of 3 of the problems. I guess manometry is one of them, and I suppose it's useful to remind you that the manometry equation, if you're going through a fluid, I'm trying to do this. So if you have a U-tube that defines the system, and you want to go from one point to another, then you know that you could write a streamline to do that. And we've made this point before, that Bernoulli equation could be written between those 2 points. And we know that if the fluid in here is static, then we can immediately get rid of both of these because they're both equal to 0. And we're just left with those other 2 terms. And so the manometer equation, if you wanted to think about it, in this particular case, we could just multiply by unit weight, P1 plus Z1 gamma 1 is equal to P2 plus Z2 gamma. They have to be the same unit weights in this particular case. And so if we write it in the way that we would do this before, we would just merely convert this into P1 plus Z1 minus Z2 gamma is equal to P2. And this, of course, would be Z1, and this, of course, would be Z2. And so in this particular case, it would say that in going up from this point to this point, we're subtracting a unit weight times the elevation change, which is the manometer rules. So it's probably easier to think of the manometry equation as you write it from one point to the other. And you'll remember that if we go down, we add pressure. If we go up, we subtract pressure. If we're in a gas, which we won't be, then the unit weight goes to 0. And if it's evacuated, then we use the vapor pressure of the system. These ones don't matter for the purpose of this exam, but going up and down in the system and writing the pressure changes between 2 points is something that perhaps you should look at. Okay, so that covers 2 out of 3 of the equations. The final one is Buckingham PI. And typically, these are defining non-dimensional variables, but also using them in some interesting way. And so we know that we can define a total of dimensions that describe the system, which are mass, length, and time. We can define a number of variables in the system. So for pipe flow, it would be viscosity, it would be pressure, it would be length, it would be diameter, it would be roughness, etc. And so we know that from these 2 relationships, the number of pi groups is equal to n minus k. And so if there are, for instance, all 3 mass, length, and time included, then that would be, sorry, that's not right. So if there are all 3 of mass, length, and time included, then this would be 3. And if there are 5 variables, then the number of pi groups would be equal to 5 minus 3, which is 2. So we can always do that. Typically, in defining behaviors, we define, say, length as some function of diameter, density, and velocity, for example. Typically, an expression or a relationship will be defined that way. And if we have that, then we can always define a pi group as being equal to the variable L to the power 1, the variable D to the power A, the variable density to the power B, and the velocity to the power C. And all that Buckingham PI gets us to do is figure out what A, B, and C are as a numeric value, and then resubstitute in these to identify the form of this non-dimensional variable. And so you've done it before, and so you can see that directly. Then typically the next dimensionless group would be that viscosity is some function of those same repeating variables, which always, if you look at prior exams, you're given. So the second pi group would be in terms of viscosity. And again, you would use the same repeating variables to find out what the exponents are of this dimensional relationship, and then define it. So once you have all of the non-dimensional relationships that define your system, then you can use those by keeping some of them the same while you change the others, and be able to define the system without knowing the equations which control it. And typically that's done by using similitude, and similitude comes in three forms. There is geometric similitude, where the various lengths of the model are equal to the lengths, the ratio of the lengths of the model are equal to the lengths of the prototype. And this is constant. So in other words, if you shrink one dimension down, you shrink all dimensions down by the same amount. In terms of kinematic similitude, then typically the Reynolds numbers of the model is equal to the Reynolds number of the prototype. And that means that the flow systems, the flow system geometry are the same. So in other words, if you have flow around a cylinder changing from viscous flow which hugs the cylinder to breaking away from it at the back of the cylinder, then that is usually indexed in terms of the Reynolds number. And so you want the Reynolds number between your two systems to be typically the same. And if that is the case, then you can use dynamic similitude. To make sure, which usually requires that the Euler numbers of the model is equal to the Euler number of the prototype. And that makes sure that the forces acting on the system, on the two system forces, are linked. So in other words, you can use the model and measure forces on the model to relate to the forces that are applied on the real structure. So if you know what the forces are in a model airfoil, you could calculate what the lift, for instance, would be on the real prototype airfoil. So I think that's it. I could go through more and spend more time doing this, but probably you're better off with fewer equations and more equations. But these ones certainly cover all the things that you need to be able to understand for this midterm. Okay. Happy hunting. Okay, thanks very much.